Okay, welcome back. We'll continue with our discussion about linear block codes. I will give one example which will make things a little bit clear. This is an example of a famous linear block code. Okay, these are called Hamming codes. So in Hamming codes, we have a parameter, an integer, positive integer with value at least 3. Okay, and then these are the parameters. The number of message bits k is taken to be 2 to the power m minus 1 for a particular m. It will become more clear when I will take particular value of m. And code length n is taken to be 2 to the power m minus 1. Okay, so definitely the number of parity check bits that is n minus k. So when you subtract n minus k, 2 to the power m minus 1 gets cancelled, so it is m. So m is actually the number of parity bits you want to add. So as an example, if we take the value of to be equal to 3, that is we add 3 parity bits, we will get k is equal to 2 to the power 3 minus 3 minus 1, which is 8 minus 4, which is 4, and n is 2 to the power 3 minus 1, which is 7, and definitely the number of parity bits m is 3. See, there is one way to write. So when message bits are, the number of message bits is k and code word is n, we also write as nk code. We call it nk code. Okay, this is a terminology. So this Hamming code is called 7/4 code. It means message bit length is 4 bits, code word length is 7. And there is one more important thing about terminology. We are taking 4 bits at a time, 4 message bits at a time. In other words, we are taking a block of bits. I will tell you later an example of convolutional codes where we don't take 4 bits or k bits at a time. We take 1 bit at a time and do some coding. So for that reason, this is called block coding. So linear because we are taking linear combinations of messages. Block because we are taking block of message bits, not just 1 bit. Hence they are called linear block codes. And if the number of message bits and number of code word bits satisfy this particular mathematical structure, they are called Hamming codes. And the generator of this code, generator matrix, of this code is defined as, see, generator matrix, you have to be, just try to understand, it has a structure p I k. Okay, what is significance of p? The significance of these rows of p, okay, so this is columns of p, right? So whichever bit is 1, actually that particular message bit is XOR together. Suppose if I have a G of this structure 1 1 0 0 1 1 1 1 1 1 0 1, then I have IK 1 0 0 0 0 1 0 0 0 0 1 0 0 0 0 1. Okay, now what does it mean? See, if we want to generate a code word, you have to do m times g, right? For a given message bits. So what it does is, you see this way, this bit is multiplied by, so if you look at this, m0, m1, m2, m3, right? And then this is 1 0 1 1 1 1 1 0 0 1 1 1. Then there is then identity matrix, right? Now this m0 gets multiplied with 1, m1 with 0, m2 with this. So what you get is m0 plus then 0 plus m2 plus m3. This is the first parity bit, and the bits of columns of parity part of generator matrix decides that first parity bit is generated by adding which message bits. Similarly, in the second column, right, you first three bits will be XORed, m0 plus m1 plus m2, then m1 plus m2 plus m3, right? And the identity matrix, what it does is you get back the code word. You get back the message m. Okay, so as an example, let's take trivial, this is 0000. This is also message. Definitely you just try, you will get code word as all 0 code word. Now take another message, suppose 0001. Okay. Sorry. So what will be the code word? So 0001 multiplied by this matrix 110 011 111 101, then 1000 0100 0010 0001. Okay, just multiply it and verify that you will get 101 0001. See, first three bits are parity bits. This is the message bits as it is. Hence they are called systematic codes. I will repeat. Systematic code is in which a part of code word is exactly replicated as a message. There are types of codes which are non-systematic. One of the examples is convolutional codes. I will give you one example at the end. So that is a non-systematic. Okay. Similarly, suppose I will take message as 0101. Okay, and again you have to multiply the 01 to obtain code word. That is why it's called generator matrix. Multiply message, pre-multiply the message vector with generator matrix, it will generate the code word. Hence the name generator matrix. 110 011 111 101 and then 1000. I hope computer science people are enjoying it. They take 4 years to play with zeros and ones. So these lectures, especially error control codes, it should not be of problem for them. Okay, so just multiply a simple matrix multiplication and you will get 110 0101. So first part, these are the parity bits and this is the message bit. So this is B M, this is your code word. Okay, so there is very important property of code words, that is something called Hamming distance. You will see that it has a very important impact on the error performance of code words. Hamming distance. What is Hamming distance? So I will define it. Suppose you have two code words C1. I am writing C1 vector and C vector are two code words. Okay, of course they have same number of elements. They are both 1 cross n, right? And Hamming distance is denoted by CD of C1 comma C2, and it is defined as number of locations in which their respective elements differ. Okay, so as an example, if you take the same C1 as, suppose I will take the above code word C1, I will take as 101 triple 01 101 triple 01, and C2 as 110 010 01. Okay, now what is D of C1 C2? So at first location 1 1, no, it doesn't differ. At second location they differ, so 1. Third location also they differ, plus 1, then same, then again they differ, plus 1, then same and same, so 3. So Hamming distance is 3, because at 3 locations these two code words differ. Okay, so this is the Hamming distance. There is other terminology that's called Hamming weight, other quantity rather. Hamming weight we denote as W of C. Hamming weight is defined as number of non-zero elements in the code. Okay, so again, Hamming weight of C1 of this example. So how many non-zero elements are there? 1 2 3. And Hamming weight of C2 1 2 3 4 4. Okay, and there is very important thing. See, there is a all zero vector, so I will note that as 0. All zero code. This is corresponding to message 0000, right? If you take any other code, suppose 110 110 11 1 2 3 4 5 6 7, okay, you take any other code. So if you take the Hamming distance of any code with 0 code, what will you get? So definitely it differs here. It differs here too. It is same here, so 1 plus 1. So then differs here plus 1. It differs here plus 1. Same. So differs here plus 1. So this is 5. Right? And if you see the Hamming weight of this C, this is also 5, because there are 5 non-zero elements in C. So in other words, Hamming distance between a code, any code, and 0 vector is same as Hamming weight of the code vector. Okay, and there is an important quantity which we will introduce later, that's called minimum Hamming distance. But right now, for us, this example is sufficient. Okay, now we will study. So this part is encoding part is quite clear now. Okay, just let me just tell you one more thing. How to design a hardware for encoder. See, this is the property of beauty of this error control code. It directly gives you hardware design. Actually, hardware design can be easily realized by looking carefully at the generator matrix. Look at it. 1 0 1 1 1 1 1 0 0 1 1 1, then 1 0 0 0 0 1 0 0 0 0 1 0 0 0 0 1. Okay, now what will be done by hardware? Hardware will first have a registers, 4-bit register, where you will store M0, M1, M2, M3. You might have done this, you should have done this in digital electronics. So at NIT Srinagar, as well as at I know some universities, digital electronics is part of syllabus of BTech in ECE, computer science, electrical, all the 3 branches. So no excuse by anyone that I am from CS background, I am from electrical background. Now these are registers, so they can be realized using D flip-flops or D latches using hardware. Now I want to generate parity bits. So in this particular case, so you look at this, So it is 1011. This corresponds to M0, M1, M2, M3. To generate first parity bit, I have to take M0, M2 and M3, right, and XOR it. So XOR gate, again hardware realization. This is your B0. Nice. Let me use now different color for second bit. For second bit, you have to take M0, M1, M2. So let me take it. I can take it like this. And XOR it. And you will get B1, right? Then you have to take M1, M2 and M3. So let me take it with the blue color. M1, M2, M3. Again XOR it. You will get B2, right? And rest of the bits you have to take directly. So that is M0, M1, M2, M3, and this again you have to put a register here, 7-bit register. And this is your code word: C0, C1, C2, C3, C4, C5, C6. Okay, later we will see something called cyclic linear codes. They provide even better hardware realization. But this also, so you need 3 XOR gates, you need a 4-bit register for message and a 7-bit register for code word, and you can design your linear block code. It can be done easily in lab. It can be implemented easily in on any FPGA also. Okay. Now this much for coding. What about decoding? That is, what about errors? How to detect and correct the errors? Okay. See, for encoding, you use it generator matrix, right? For decoding, we had to use H matrix, which was defined to be I of n minus k p transpose, right? This is called parity check matrix. It will be very clear soon that why it is called so. And for decoding, so I will draw a block diagram that will be more clear. So here is the M, it is the message vector. Here is the generator matrix. And you get a code vector, right? And what is the property of this? So you know that we proved this property in the previous video. You just recall about the parity check matrix and generator matrix. That was Hg transpose is equal to 0, and which immediately gave us Ch transpose equals 0, right? So you can write here code word bit. Here is the parity check matrix, and you get here null vector, right? Nice. Now when you transmit this code word over the channel, assume the discrete memoryless channel. What will discrete memoryless channel do? 0 may get changed to 1, 1 may get changed to 0. So what you receive at the receiver, you will not receive the code word. It will be a code with errors that we call as R, received vector. So R is a 1 cross n received vector that results from sending the code vector C, okay, over a noisy binary channel. Okay, now suppose so how can we realize the error? You see, suppose your code word was 1010011. Suppose this is the code word, and let's say when you transmit it over the channel, there is an error at this location. This 1 gets changed to 0, so you receive 1000011. This can be realized in this way. It is equivalent to saying that, how is this error realized mathematically? That as if this code word got added by this message 001 0000 and you XOR it, right? You see, the XOR of these two is this message, which is the errorful message. This particular sequence of bits where we put 1 only at the location where error has occurred, it's called error pattern or error vector. So in general, this received vector can be realized as XOR of or modulo to addition of code word and error pattern, error vector. So this error vector has elements, same number of elements, E0, E1 up to En minus 1, and its elements take value Ei is equal to 1 if an error occurred in ith location, 0 otherwise. Now what is the task of receiver or decoder? Task of receiver here, channel decoder, is to decode the code word C from received vector R, right? For that, we will compute an important quantity. See, if you have a code word and you take CH transpose, it is equal to 0. Now you at the receiver, you don't have code word, rather you have this received code word, RH transpose, and definitely if there is an error, it will not be equal to 0, right? But it contains some information about the error. So RH transpose is a very important quantity, and it is given a very separate name called syndrome. There is some reason behind it. It was used in some DNA, RNA sequence encoding, and hence it is given the name syndrome. Okay. Okay, it's a very important vector. It tells us a lot of things about error. It has some properties, very trivial properties. So let's see the properties of syndrome vector. Okay. The first thing is that, let's write it. So S is RH transpose. R is code word plus error pattern H transpose, which is CH transpose plus EH transpose. CH transpose is 0, and what remains is EH transpose. Okay, this is one important thing. So we can say that syndrome depends only on error pattern and not on transmitted code word. Okay, that is one thing. Second property is more remarkable. I will first state that all error patterns that differ by a code word have the same syndrome. Okay, all error patterns that differ by a code word have the same syndrome. Now, what does it mean? Let me first tell you one thing. See, you have a message which is you have a message which is k bits. So you can have total 2 to the power k messages. Your code word C is actually of n bits. So actually you can have 2 to the power n codes. Since n is greater than k, but you have only 2 to the power k messages. So corresponding to each message, you have one code word. So you have actually 2 to the power k codes only. Right? Now, if I have a code word, suppose Ci, code word vector Ci, for I is equal to 1 to 2 to the power k minus 1. Right? These are the, so it is one of the code words out of 2 to the power k code words. And you have an error pattern, suppose E. Okay. Now, if you add this E with any of the code word, right, you will get another error pattern. Okay, for I is equal to 0, 1 up to 2 to the power k minus 1. Now you see, you have a set of vectors ei, right, and this is called coset of a code. Okay, so you can say actually coset has exactly 2 to the power k elements. Right, you can have 2 to the power k different cosets that differ at most by a code word, right, because ei is equal to e plus c. Okay, and it has one important property. You see, if I take this ei is e plus ci, if I post multiply by h transpose, so ei h transpose is e h transpose plus ci h transpose. So ci h transpose is 0 because they're code words, so e h transpose. So you see, ei is the error which differs from the error pattern e by code word. All such error patterns have same syndrome, right? Have same syndrome. So this is one important property. And one important quantity for error correction is, you already know now, Hamming distance, Hamming weight. So there is something called a minimum distance of a linear code. Minimum distance of a linear code. So it is the smallest Hamming distance between any pair of code words. D minimum. Okay, we will see it has very important impact on error correction capability, and it is same as the smallest Hamming weight, because Hamming weight at the end, you have seen Hamming weight of a code is nothing but distance, Hamming distance of a code with 0 code. So hence minimum distance of a code with 0 code, so You take any code and then check which code has minimum distance with the 0 code. That code will also have minimum Hamming distance. Okay. Now I will realize the codes in some abstract geometrical space. Okay. Suppose here is a code word. Just wait. Suppose here is a code word CI, and here is a code word CJ. Okay. And let's say that we need a proper, that is, we need to design NK code, okay, such that it should correct all error patterns over binary symmetric channel, that is when binary errors are there, whose Hamming weight is less than or equal to t. Okay, so that is at most the Hamming weight is t. There are t number of, at most t number of bits which are non-zero. Okay, now what we can do is, so if we draw a circle or a sphere around it and it has a radius t, okay, and similarly around this it has a radius t. If you choose code words such that they don't overlap, right, then suppose you transmit CI and the received vector stands here R. There is an error, but it is here. There is another scenario which is like this. Suppose this is CI and CJ. Of course, since its Hamming weight is at most t, so this is it's like a radius, we take at most radius. Now if there is an error and received vector falls here, so there is no way to correct the error. See, in this case we know that received vector is still here in this sphere, so it is CI code word which was transmitted. But if code structure is such that, okay, the Hamming distance between the codes is such that the received vector falls at the intersection of two codes, then we cannot correct the error. So Hamming distance, what is the worst case? Worst case is that they are just touching each other. So this is T, this is T, this is CI, this is CJ. So Hamming distance between the two codes should be CI CJ. It should be greater than or equal to how much? So actually it should be strictly greater than 2t, right? If it is less than 2t, this is the case of less than 2t, right? Then it will be, there will be intersect. We may not be able to correct all the errors. So in particular it will be greater than or equal to 2t plus 1, right? Because we are dealing here with binary bits, so we are counting them. So if it is greater than 2t, then it has to be greater than or equal to 2t plus 1. So this is an important design characteristic of a code. If you want to design a code, it should satisfy this property. Okay, and it will be able to correct all t errors. That is very important. See why? Because suppose if you look at this, right, here is a code word. If there are t errors, since t is the Hamming distance also, Hamming weight of this code, so if there are t errors, your received code word will stay at the border, so you will be still able to decode it. But if there are more than t errors, then received vector will be outside the circle, right? So this code which satisfies this property, that Hamming distance between the code, any two code words, is greater than or equal to t plus 1, will be able to correct T errors. In other words, if you want a code which can correct T errors in the code, you need to have Hamming distance between the any two code words at least 2t plus 1. Okay, so it means that the minimum distance, Hamming distance, should be 2t plus 1. That is the significance of minimum distance, right? And if minimum distance is 2t plus 1, then code can correct all errors. How many? D minimum minus 1. Okay, since d minimum minus 1 divided by 2 can be fractional also, so I will take this integer part. Okay, largest integer part. So these are some of the properties, and now I will demonstrate the syndrome decoding property. So we will discuss that syndrome rules and also demonstrate with one example in next lecture.